Yeah, cool. Thank you, Niven. Yep. Just before we get started, any new members in the last month or two? No hands up. Oh, yes. Hello, welcome. It's always nice to see new faces. Did you get a handout? Yeah, you got a handout. That's cool. Okay. I think we're right. Lighting's about good. So let's get underway. Thank you very much for coming out, everyone. Okay. So this here is an image of the sun. You probably know that. If you asked an astronomer and said to them, hey, give me 2 interesting facts about the sun, and they might say to you, oh, well, it's got a surface temperature of 5,800 degrees, and it's made up of about 98% hydrogen and helium, with about 2% of mixture of other heavy elements. You might think, whoa, how do they know that stuff? For Pete's sake, the sun is 150 million kilometres away. How do they get information from something so far away? And then they might say, oh, that's nothing. You know, we're now detecting and looking at atmospheres of planets going around other solar systems, other suns. You know, you're talking tens, hundreds, up to 1,000 light years away. You know, billions of kilometres away, and they're getting this information. Holy moly! You know, so how are they doing that? And you can see they're literally thin atmospheres, just billions of kilometres away. How are they doing that? And that's why today's talk is titled Stellar and Exoplanetary Spectroscopy, learning to read the light, where we're going to learn and we're going to answer the question how and why astronomers split the light from distant stars and galaxies. First of all, let's start with a little bit of history. And it was this guy here, a French philosopher by the name Auguste Comte. I think I pronounced that right. I think you're the French. Yep. So the 1830s, and his quotation that he was very famous for is, science will never be able to understand what stars are made of because they are so far away. Famous quote. And this guy here, William Huggins, came along and blew that out of the water about 30 years later. And he was the one who pioneered this very relatively new instrument called the spectroscope. And he pointed up to the heavens and started finding out all this new information now about stars and galaxies and so on. And that really has changed astronomy hugely. So I've split it up into these main chapters here. We're going to start really from scratch. And I said in the email yesterday, this is for beginners right through. We're going to start right through with atoms, what atoms are, how they give rise to light, and what spectroscopy is. Then we'll talk about how they use spectroscopy to determine the temperature and composition of stars. We'll then talk about the stellar radial velocity, in other words, how fast a star is travelling to you or away from you, and how they determine the rotation of a star rate, how quickly it's rotating just by spectroscopy. We'll then get a little bit more advanced and we'll talk about surface gravity, the strength of gravity on the surface of a star, magnetic field lines in the stars, how they can assess those with spectroscopy. And then we'll talk about the new exciting area of astronomy, exoplanetary atmospheres. And then we'll wrap up and summarise the main points. So that's our roadmap where we're heading tonight. Okay, let's start with atoms, light and spectroscopy. So we're going to talk about what atoms are and how they give rise to light or how they can absorb light. We'll talk about the importance there of that sort of rainbow pattern, the importance of that to us. And of course, if you're looking for a pot of gold, that's what you want to be looking for. So let's start with this. Atoms are the building blocks of everything. Remember last month, I think we talked about how cells were the building blocks of life. Atoms are the building blocks of everything. And this is a very simple, very simplified model called the Bohr model of the atom that we've probably all learnt in school. And you can see here it's got a central nucleus with a positively charged neutrons that are green here and in red here, representing these neutrally charged neutrons. And then in blue here you've got these shells or orbits, if you will, of in blue here of these negatively charged electrons. And you have a very small central nucleus with an outer shell of electrons. It's a very, very crude model, but a wonderful model for explaining the principles of behind it all atoms. And just a little term here that we'll use a few times, it's just nice to know about, is the inner shell, that's this one here, is known as the ground state of electrons. It's the state where the negatively charged electrons are at the closest to the positively charged nucleus, so at the most stable and lowest energy state, and it's known as the ground state. And just look a little bit further about atoms in general. So they are dictated by hydrogen, carbon, nitrogen, and oxygen, just four of the common ones here. And they're dictated by which element is by how many protons you've got in the middle. And there's hydrogen. Hydrogen's got one proton, doesn't have a neutron, or has isotopes of them, but the basic one just has one proton and one electron. And you can see here, for example, carbon, you've got 6 protons and 6 neutrons and 6 electrons, and then nitrogen and oxygen with increasing numbers and so on. And it is the number of protons, as I mentioned here, in the nucleus that determines what elements you've got. And it is the arrangement, the numbers and arrangements of the electrons around the outside that determine the chemical properties of atoms. And that's what we are really focusing in on shortly. So here it is here. Here is, for example, an atom. Could be a hydrogen one, for example. Here is your electron in the inner shell, and it's nice resting quietly in its ground state, and the electron remaining nice and close. Now, electrons can absorb light or absorb energy in the way of light, for that matter, or with a collision with another atom to be excited to another area. So an electron could get bumped here up to a higher level. So if it moves away up to a higher level, is it absorbing or releasing energy? Absorbing, yeah, it's absorbing energy, exactly, to move up into a higher level. So here it is here, and all it takes is a specific photon of light, particle of light, or, as I mentioned, a collision will do the same as well. It's imparting energy, and the energy lifts the electron up to another level. So when it moves back down again from that higher level, back down to its ground state again, it's going to absorb or release energy. Yeah, releases energy. Yep, exactly. And there it is there. Eventually it will want to go back to its natural stable state. So it might get hit by a light, particle of light, or a collision, and takes that energy, moves up, and when that stimulus is gone, it naturally wants to fall back to its most stable, lowest energy state, and it gives off light. The main thing here is each energy level for each different atom and between each different level is unique. The energy levels and the amount of energy required to bump it up or bring it down is unique for each excited state of each atom. For that reason, they call it a fingerprint. So if all these were different elements, for example, they would all have, the moving from the first to the second would be different from the second to the third, which would be different from the third to the fourth. All these different combinations you can think of. And all those combinations here would be all completely different for a different atom and different for atom here. So each moving from shell to shell, and any combination you like, for any different element you like, all of them are different. They're all unique amounts of energy. And then if you get impacted really with a large collision or a large amount, say some ultraviolet light or something like that, and you bump the electron straight off, that's called ionization from a high energy collision. And the atom is then called an ion, and it's annotated with a positive sign because it's lost the electron completely. For example, calcium goes to calcium plus, or in this case, if you lost 2 electrons, it becomes calcium plus. And there it is there. That's sort of how you might annotate it. You'd put a 2 plus up here. So that's called ionization. That's just taking it to the next level where, never mind going up to levels, you've kicked it right off. So that's our basic model of atoms, the Bohr model of atoms, and to explain things. So let's talk the next thing about, we've mentioned light. What actually is light? And the bottom line is, this diagram shows it, light is essentially, it's alternating waves perpendicular to one another of electric and magnetic energy. And that's essentially what they are. Magnetic fields and electric fields perpendicular to one another in a wave pattern. And light has a very important property called the wavelength. And you can either run it whichever way you like, from peak to peak, or you might run it, for example, from trough to trough. But either way, as long as you're consistent with it, and that's called one wavelength. And it's a really important property of light. Why is that? Because light comes in a wide range spectrum called the electromagnetic spectrum. And in the middle here is a good enough place to start. You see what we call visible or optical wavelengths, visible light here. And this is the whole spectrum. And as you get more and more energetic, you go up to ultraviolet light. It causes your sunburn and your skin cancers. X-rays when you've broken your bones, and more powerful ones up to gamma rays. And here you go to infrared, like a lot of remote controls, your microwave and your radio waves. And you notice here, as the energy gets less and less, the wavelengths get longer and longer and longer. So longer wavelengths, lower energy, and going this way is the wavelengths get shorter and shorter and shorter, as shown here, and the energy levels get higher and higher and higher. And it's this visible one here with wavelengths from about 400 to 700 nanometers that you get our visible light, which then gets splits up into all the colours of the rainbow. So the next question is, how can we disperse, how can we do that like you see with a rainbow? How can we disperse that white light into its various colours? We do it because light, as you saw, is a wave, and waves have properties, and there's two relevant properties to this here, which we'll talk about, which enable us to split the light up with either a prism or a grating. First of all, a prism. You've probably all seen prisms before. You've all got Dark Side of the Moon's LP at home, Pink Floyd. So a prism there is essentially, it's a transparent solid with smooth angled surfaces, and just looking at its side on here, and as light travels towards it, because it's transparent, but it's a different medium, it might be glass or whatever, and light bends. One of the properties of light is when it hits a surface at an angle, it bends, or refracts, and it goes like that and then goes again like that. And the thing is, the key to it is that different wavelengths bend at different angles, and that's the key. So your blue one's up here, that's a very short wavelength, and it's higher energy, right down to your red, which are longer wavelengths here. So that prism is able to split them up simply because the different wavelengths refract and bend at different angles. So that's how a prism works. And then there's what we call the process of diffraction, and you can get a diffraction grating. And essentially what you've got is, the property here that we're relying on is another property of waves, is that waves tend to bend around edges. So you get a sharp surface, and you get little fine edges. Light bends around the edges. And this is a grating here, and you've all got many, I'm sure, in your collection at home. You've got loads of gratings at home. Your basic CD or DVD. It doesn't have to be an Elton John one, but it helps. But you've shown this up to the light, and you see all the different colours it shows. There's millions and millions and millions of little tiny little microscopic grooves in there that when light strikes it, they all get reflected off at different angles. So that's the diffraction and the prism. And it is an instrument known as a spectrograph that either with a prism or a grating or both that the astronomers use to split the light up into all its various wavelengths. And spectrographs come in all different shapes and sizes depending how big your pocket, how deep your pocket is. This is the HARPS in the Atacama Desert, and that's, of course, multi-billion-dollar apparatus. That's the main sort of telescope there. The spectroscope, I think we showed at one of the last meetings, it's sort of huge, big things in a vacuum chamber. So that's worth millions of dollars. Then you get your home kit. And this one here, this is my one here that I bought, just called a star analyzer. It's a diffraction, essentially a diffraction grating, transmission one where light goes through here. You just screw it onto your telescope, and the reason I brought this in is just to show you how simple, and you can do this at home. This just simply screws into here like that. Whoops, let's grab that. Yep. Oh, it screws onto here. This is a little a CMOS or a CCD camera. Screws into here. You pop that slides down into your telescope. Cable goes from here into your laptop sitting by your side, and I'll show you shortly how it's all set up. So I'm going to show you some simple stuff, and Victor here, who I lent this to, he's done some great work with it, so I've got some of his stuff as well. And to show you how really available this is, Martin lent this to me for tonight too. This is a little cheap, very accessible. You buy these as a little spectroscope that you can attach to your telescope as well. So these things are out there. They're not just the toys of the big boys. These things are readily available. Thank you, Martin. That's my little setup at home, just to illustrate how basic it is. So here's my star analyzer, my grating. That's it here, and the camera and the cord just going to the laptop, and that's just sit up in the backyard at home. So that's all there is to you. All the stuff that we're going to be looking at, you guys can do quite happily, and it is a lot of fun. So that's a little bit introduction to spectroscopy and atoms and light. Let's move on to how you tell the temperature and composition of stars. let's get into the nitty-gritty of it with spectroscopy. And essentially, we're going to be looking at some raw data in a minute. You get that, and your computer, you get software with it, and the commonest one called RSpec by a guy called Tom Fields in the US, and it's very affordable sort of software, and it will quite happily construct one of these, what we call a spectral energy distribution curve like that. And it's really a plot of, you got the wavelengths all along here on the horizontal x-axis, and the intensity of the light recorded at specific wavelengths here. And here's, of course, is to your 400 to your 700 nanometers. That's your visible light there. So, yeah, so an SED, as it's known as, spectral energy distribution, is a plot of light intensity versus each detected wavelength. And this interesting stuff, it's the shape of these curves here that you can determine the star's temperature with. And you see these are all labelled, but I'm just going to go down to the next one. So there's two things. With increasing temperature, you'll notice two things. So here's these nice SED curves. Here's for a star that's got a surface temperature of 7,000 degrees, 6,000, 500, 4,000, 3,000. And you'll notice two things. One is the peak wavelength increases intensity as the increased temperature of the star. So for example, this one here, say that's got a surface temperature of 3,000 degrees, the peak is here. It's not very intense at all. But as you go up to 4,000, 5,000, 6,000 and 7,000, you notice the peak is labelled with an X. So that X peak is getting higher and higher. So the intensity increases with the peak wavelength. The other thing you've probably already spotted here, you can see with where these X's are, is the peak wavelength decreases. Remember, wavelength decreases, the energy of the photon of light increases. So you'll see here, so once again, as you're increasing the temperature of the star, you notice there's a trend here as it goes up, but it's also moving more and more to the left, to the shorter but more higher energy wavelengths. And it's the shape that indicates the surface temperature. And here's another little diagram. Here's a very hot blue star, temperature of 8,000. You notice the peak temperature is up here in sort of more the blue wavelengths, and it's very high up. Going down to a yellow star, for example, our sun, spectral type G, there it is here right in the middle. It's peak wavelength, and it's of yay intensity. And a cooler red star, you're really getting down into the infrared wavelengths here, and once again, a low intensity. So those are the two things that give you an idea. Now, we're going to move on to it shortly. That gives you a sort of rough idea of the temperature of a surface of the star. But there's other things in here called spectral lines we're going to talk about, which gives you a more detailed, there's another method you can use to determine the temperature of a star as well, which is a little bit more accurate. So, yeah.
What do you measure intensity? What units?
Oh, okay. Look, I'm unsure what the units in here. Usually it's probably watts. Yeah, I'm unsure exactly what they. I haven't done that for a wee while. Okay. Actually, we will find that out shortly. So there's cool things called Wien's law, and this is how they use it to actually determine the temperature. This is a guy here, Wilhelm Wien, and from the 1800s, and he got this formula together. So the temperature in Kelvin is the constant 3 times 10 to the 6 divided by the maximum wavelength in nanometers. And we go through here. So for example, this is an example for our sun. Let's calculate the temperature of our sun. So this is the line here for our sun. I've just got rid of all the other lines to make it simple, but here's our sun here. The peak comes in at 517 nanometers. So that's it here, 517. So let's plug that into the equation. Is it there? And that comes out to 5.8 times 10 to the 3, or 5,800 Kelvin. So that's a very simple formula. That's really easy to do. The software creates that graph. All you've got to do is just point your telescope there, and with your grating filter there on, the computer does all the rest, prints it out, and you can actually calculate. And you get a little bit of a buzz out of it too. It's fun. It's really, really fun doing spectroscopy. So this is some of the raw data. This is some of the stuff that I've just done, some crude stuff here. So here's Rigel, it's a blue supergiant, temperature of 11,000, and that's that sort of spreads the first order there, spreads out the colours. And you just take my word there, but it's actually the peak brightness is in the blues in there. But we're going to show you shortly how the graph works all that out. Sirius, an A-class dwarf, 10,000 degrees, and you've got a couple of orders here. But you notice that the peak is moving across, and there's Betelgeuse here, red supergiant. You notice the red part is a lot more brighter. So that's the sort of data that the image that you see on your laptop screen. And this is the graphs. Now this graph is from Victor here, has done this. He's very, very good at this. That's why I've used his stuff. He's very good at it. But this is the stuff that your computer then automatically spits out for you here. So here's your graph, your spectral energy distribution graph here. Here's your peak up here. So this is off Canopus. Its peak wavelength, and this shows it's 475 nanometers. Put that into Wien's equation, and you've got a surface temperature of 7,350. You've worked that out for yourself. So you don't need someone looking at Wikipedia. You say, don't tell me what the temperature is. I'll work it out myself. Thank you very much. So you can do this stuff, and it's fun. And then you'll notice all these dips in here too, which we'll talk about what these are as well. But you can see you can do all this. This here costs about $250, one of these. I think Astrons probably has them, or Benton, there's a few places. Martin, where did this one come from?
That one came from South Africa.
Oh, right, yep.
At the time, it's more or less retained its price. It's yours for the thick end of about $20 to $25.
Right, there you go. They're very affordable and accessible, these instruments, to do this. Okay, so here's RSpecs, the software to do all this. Here's Sirius, so that was just some raw data there, what it looks like on your laptop screen. This is when you go back inside with a cup of Milo, and you start doing all this, sitting down and working, putting it through the software and stuff. And this is the sort of graphs that you get there. So it's all pretty straightforward how you do it. So there's that. And then let's move on a little bit now there's 3 different types of spectra, which you may well have heard of. And so let's start with the first scenario. So you've got a bright light source here. Let's say it's a bright star. And you're just off to the side and you're just looking at everything straight towards you. You can get what we call a continuous spectrum. So just a continuous bright light here, and it's got all the different colours, all the different wavelengths emitted by that bright light source. Then supposing this light from this bright source is here, and it starts lighting up all this gas, all these little atoms are getting excited, and of course they get excited, and what happens to electrons? They then want to fall back to their most restful ground state, stable state, and so they start giving out lights at specific little spikes of light here at specific wavelengths, what they call lines, and they're called emission lines, or that's called an emission spectrum. So that's looking side on at a cloud of gas and dust that's been illuminated. And then supposing you're over here looking at that gas cloud through from the light coming through from this light source here. So here what you see is the atoms are absorbing that light to get excited. So you see these lines here, what they call absorption lines through here. And on the graph, as you saw in Victor's graphs before, you get these nice little dips in here. And they represent these little lines through here. In fact, if you go back through here, you can actually see them. Yes, there you go. Yeah. You can very crudely, but you can just see little wee lines running through there, and they correspond on the graph. They're called absorption lines. And as mentioned before, the wavelengths of these absorption lines, each one corresponds with specific elements and molecules and specific energy states. They call it like fingerprints. You look at what wavelength it is, and you can immediately tell what atoms are there and what excited state they are in. So why do you get absorption lines when you look at stars, like for example the sun? And the reason you're getting that is here's the hot interior of the sun here with all its energy blazing out, but you've got a cooler, less dense atmosphere out here full of more sort of sparsely spaced atoms, and it's those atoms out here that are absorbing the light from the heat of the sun. And so when you look at the sun, or any star for that matter, you get these dark absorption lines from the atmosphere of the star that you're looking at. So let's just go back to these here. And as I mentioned before, because this is just key to it all, I think that's why I've repeated here, these are fingerprints of specific elements, and you'll see molecules shortly at specific energy levels. And you're usually looking at these spikes, or you're looking at dips. Okay, so this is what we call hydrogen has various lines, but I use this as an example. You may well have heard of Balmer lines, and Balmer lines refers to, so here's a hydrogen, your proton in the middle here. Here is your lower ground state, they call it n equals 1, and here's your next level up, n equals 2, and whenever you excite an atom, it absorbs, goes up to various levels, or if it's already up here and going down to the second level there, it gives out these what we call hydrogen Balmer lines at specific wavelengths, and you can see them here. So that's because your hydrogen, of course, is the most common element. That's why I bring it up here. Stars are full of hydrogen, and you're going to be looking in the visual wavelengths, optical wavelengths. So when the electrons go up or down from the hydrogen's second energy shell, you get what we call these Balmer lines. That's an important little thing, because you probably will, with your reading, you'll bump into the word Balmer lines, and you'll wonder, what is that all about? So there's a whole stack of things for hydrogen, and this is a nice little principle. So here's your Balmer lines, going from the third down to the second, fourth down to the second. So each different combination comes out at different wavelengths. So going down to the first ground level, of course, that's going to be giving out or absorbing a lot more energies getting involved, because you're getting closer to the nucleus. So you get what they call Lyman series of lines, going from 6, 5, 4, 3, 2, 1, and you're getting in these different wavelengths and the ultraviolet wavelengths. And they're called Lyman series, and they're in the ultraviolet part of the spectrum. And then you might say, is there infrared ones? Absolutely, and that's jumping down, up or down from the third shell energy level, and these are in the infrared, and they're called Paschen series. So those are common ones. There's actually more to it than that, but I throw that in there just to help you get that in concept of all the different combinations you can get, and you'll bump with your reading, you'll bump into the Lyman series of lines, you'll bump into the word Balmer, and you immediately know what it is, and you'll understand why they are present in different wavelengths. Yep, so it is that Balmer series of lines is from that second shell. Okay, so here are these absorption lines that we saw earlier on, and this is the surface of Sirius, the bright star in the sky, surface temperature of 10,000 degrees, and this is what its spectral energy distribution looks like up here. So here's your peak wavelength, but you've got all these dips in here of hydrogen lines, and notice how they're really strong. They dip down quite a lot, and you can see the strong lines here, and the dips here. They're very, very strong hydrogen lines. Here's our sun, which is a little bit cooler, 5,800 degrees. And so notice that its peak wavelength here is at longer, less energetic wavelengths from the more hotter Sirius, so we're aware of that now. But notice the hydrogen lines aren't as strong. So here they are here with the dotted lines here. They're not as prominent as these ones here. You might say, what's going on here? Which we're going to have a look at, because that's all to do with its temperature. Remember I said you can tell the temperature of a star not only by the shape of its spectral energy distribution curve, but also by what atoms are in what ionized or states and excited states and so on. And this is a lovely one here. So here's our sun, for example, 5,800, say roughly about here, and that's the sort of what you'd see in our sun if you draw a line up through here. And here's Sirius, surface temperature of 10,000. Notice it's really high in hydrogen, and notice the hydrogen drops off here and it drops off here. So what's going on here? So here it is here, surface temperatures, and here's, if you draw a line down any one of these temperatures, here's Sirius, here's our sun. That's taking a cross-section of what you're going to see. So why is that so? Why is hydrogen really strong in Sirius, but it's, you get to these OB class stars over here, there's hardly any hydrogen sort of lines to be seen, and same as the really cool stars, it's just over here. So why is that so? And it is because of Sirius just has the right balance. It's the sweet spot. It's got enough collisions and photons going on, light zapping around and collisions going on, because it's surface temperature of 10,000, where most of the electrons are constantly, their stable state is the second shell. There's too much activity for them to actually go down to that first energy level shell. So most of them sit up on that second energy shell. And of course, what did we just learn a few slides ago? What does that give rise to if they get up or down from there? Gives strong hydrogen absorbent, those Balmer lines, because we're looking in visual wavelengths. So in visual wavelengths, you see prominent Balmer lines in about temperature of about 10,000 degrees, such as Sirius, because it's reasonably hot, not too hot, but it's reasonably hot. And so all the atoms sit up on that second shelf. Hydrogen features very weak in these ones here. Why? Because it's a lot cooler down here, and most atoms are not getting excited and are quite happy. Most of them are sitting still in their ground state because it's not hot enough to drive them up to that second level. So when they do go up and down, they're going to be, they're going to take a lot of energy to do that, and you're going to see Lyman lines if you're going to get that at all. But you don't see your hydrogen lines there. And here, at the very, very hot, the other extreme, where the temperature is so hot, most of the hydrogen is fully ionized. Electrons are no longer in the shells; they're floating around amok amongst with the protons. So they're mainly ionized. So once again, you don't see those strong Balmer lines. There it is here. So very cool. Fewer collisions going on to excite electrons. So they're just sitting happily there in the ground state, and in the hot state, everything's ionized, so you don't get a chance for electrons to sit around. So that's temperature and composition. So that's how that astronomers told you at the start, sun's got a temperature of 5,800 and what its composition is. And you can do that too quite happily, just buying one of those diffraction gratings and putting it on your telescope. So how about stellar radial velocity? In other words, how fast a star is coming towards you, away from you, and how fast a star is rotating. So let's look at that. And astronomers use what we call the Doppler effect to do that. And the Doppler effect is where it's another property of waves that we use every day and astronomers use as well, whereby waves of light or sound emanate from a particular source. And sound is the easiest one to use because it's more intuitive and we see it every day. That here's an example is a siren, like an ambulance, for example. If it's just sitting there stationary, you just hear woo, woo, woo. But suddenly if it starts racing towards you, it's the wavelengths of light get all compressed. And so the pitch of the sound goes up. Likewise, if you were here and the ambulance or a siren was going away from you, the wavelengths of light are getting stretched out and the pitch drops. Classic example is a racing car. As it zooms past you, the pitch goes up and it drops away. That's classic example of the Doppler effect. Light is no different. Light comes in wavelengths as well. And so if it gets compressed, the wavelengths are getting shorter. At a visible light from red to blue, what's got shorter wavelengths? Blue. Yeah, absolutely. So they call it blue shifted. And light, if it's getting stretched away from you, the wavelength's getting big. It's the other end of the spectrum. The wavelengths get stretched out and they appear more red, and the redder end. So they're what we call red shifted. So here's your visible spectrum here with your blue, your short wavelengths, and here, and it gets longer and gets stretched out to red. And that's the Doppler effect. And just to explain how they can actually measure that from here. So here's your absorption lines that you might be doing on a particular star. And here, if the star were stationary, this is where its lines would sit with its wavelengths for its hydrogen lines. If that star was heading towards you, it's going to be blue shifted. So notice all the lines are equal distance apart as they were stationary, but suddenly they're all pushed over to the right-hand side. You can see it here. They're just slightly shifted over, the blue shifted. If the star is travelling away from you, this is the spectrum you would see. Here's your absorption lines. That's equal distance, same as from stationary, but notice they've all been shifted across. They've been red shifted. And you get your calculator out, and there's a very simple formula to work out the velocity. It's how much the wavelengths have changed divided by the wavelength at rest, stationary, and that equals the radial velocity of the star divided by c, or the speed of light. So very simple formula. All you have to do is do your spectroscopy, see if it's blue shifted or red shifted, determined by how much, get your calculator out, hey presto, you know whether the star's, how fast it's travelling towards you or away from you. Okay, then, rotation. So all stars rotate, and you can measure how fast they're rotating around. Because here's a spectrum of a star that's non-rotating, and that's all fine here, and you're going to get your spectral lines are going to be a nice fine absorption line here, and you're going to have that nice sharp dip. But with a star that's rotating, one edge of it is travelling away from you, so that's going to be red shifted. The other part of the spectrum, this side of any light coming from this side of the star, is coming towards you, so it's going to get blue shifted, and the stretching out between red shifting and blue shifting absorption line broadens the absorption line there, and on your graph you're going to get a more broad, they've exaggerated here of course, but they've broadened out your absorption line here on your graph compared with that here. So once again, it's the amount of broadening of those absorption lines, very simple formula to work out how fast the star is rotating. So that's all with Doppler, which is all with your spectroscopy. So how about surface gravity and magnetic fields? Yeah, so surface gravity represents the amount of, if you're standing on the star or close to the star, how much gravity is pulling you down to it. And that is important to know with the stars, which we'll talk about. But the bottom line is, the increased mass or density of a star increases your surface gravity, which increases the density of your atmosphere down low. So you're going to get increased particle density and collisions down at the surface. So a star with, for example, low gravity, it might have a more fluffier, wider atmosphere, but if you've got a smaller condensed down star with a higher, stronger surface gravity, it's going to be pulling that atmosphere down. So the atmosphere is going to be more dense with particles and more collisions going on, which means more and faster electron transitions going up and down all the different levels, and that means you get a wider range of photon energies here. And here you can quite happily see it here. In fact, that's a normal one, and as you go here, you're stepping up your gravity, the surface gravity, and notice how all the lines are getting more broadened, and also just a much wider range. So that's the sort of pattern you'd get. That from there, they can calculate the surface gravity. And you might say, well, what is the point of that? That's very useful if you're looking through your spectroscope and you see a star and you've worked out its temperature, so it's sort of spectral class, if you will, or its temperature. But you want to know a bit more about it. You want to know, hey, is that just a relatively compact dwarf star, or is it a red giant or a red supergiant that happens to be the same surface temperature, but it's all puffed out and fluffed out? You do your surface gravity, and of course if it's really low, it suggests it's a red giant or a supergiant. And if the surface gravity shows it's actually quite high, and they'll have their formulas for calculating it, it suggests it's more likely to be a dwarf. So that is important. Then it comes down to magnetic field lines. Stars have essentially big balls of charged particles, and so they have magnetic fields and magnetic field properties. And here's these different energy levels here of the electrons we've talked about. But electrons, and quantum-wise, when you get down to quantum mechanics, they actually have 3 different quantum states, slightly subtle differences. And so instead of one absorption line, they've actually got 3 attached to them when exposed to a magnetic field, a strong magnetic field. And it's to do with their intrinsic angular momentum inside them, which is known as the spin property of an electron. Not a physical spin, it's just a property that describes how an electron will behave in a magnetic field. It's its intrinsic angular momentum, if you will. And a strong magnetic field will split those electrons up into 3 different quantum states. And of course, the increased splitting with the increased magnetic field. So it's called the Zeeman effect. Here it is here, is Zeeman effect. These what they call sublevels. So increasing the magnetic field exposes and increases the distance between splitting it up. And here's a lovely picture here. This is a sunspot, and of course sunspots on our sun are just areas of intense magnetic, more concentrated magnetic field lines. And you can see they've done a spectral line through here, and looking at it closely, and you can see the spectral lines are all split up with what they call Zeeman lines. So that's another thing that you can tell from looking at the spectra of a star, or particularly our sun. You can tell the strength of its magnetic fields. Okay, let's move on to exoplanetary atmosphere. So that's all to do primarily with stars, and all to do primarily in optical wavelengths, the visual wavelengths that we see. So we're moving on now to something completely different that's been in the news a lot recently, and that's looking at detecting the atmospheres around these exoplanets, planets around other stars other than our sun. But these things are tens, hundreds and thousands of light years away, and they're able to detect any atmospheres and actually analyse the atmosphere. So it's a slightly different ball game here. So light travelling through, any atmosphere allows analysis of its composition. insert here. So what you're looking at here, instead of absorption lines or emission lines of individual electrons jumping up from discrete energy levels like that and dropping back down again in discrete energy levels, this time you're dealing with whole molecules and chemicals going on. And what you're measuring this time is the rotation and vibration. Vibration, rotation. The molecules are always jostling around. An atmosphere is going to have a little bit of pressure. It's going to have some wind and some clouds and a little weather, if you will, looking for a better word. But it's going to have things going on. But also, nothing in this world ever sits still. Everything's at a party. Everything's partying. Even in a stable environment, molecules are partying. They're rotating, they're vibrating, they're having fun. But more so if they're in the conditions of the atmosphere. And that's what you're looking for. That gives out light, that's absorb, rotation, vibration. And that quantized as well, by the way. It's not sort of, they can rotate any which way they like. They sort of come in quantation, sort of the quantate into discrete amounts of rotation or discrete amount of vibrating as well. So that's what you're picking up. But instead of visual wavelengths, molecules vibrate and rotate and absorb and emit energy of light at the infrared wavelengths, not optical. So here's our visible wavelength we're looking at before. We're now moving down into longer but weaker wavelengths in the infrared. And of course, infamously, the James Webb Telescope is ideal for this. This is it's designed specifically for infrared. There will be better telescopes coming out with more resolution, but for now, that's our best telescope for doing this, getting good resolution. And the idea here is they do two measurements. It's not just, we've got an exoplanet there, let's see if we've got an atmosphere, let's look at the light. What they actually do is they look at the light from the star, the host star first. They look at the light from the host star. They split the light up with their spectrograph. This shows that there. And then they get the light as the planet transits across the host star. They look here and they detect an atmosphere and then spread that out here, and they get those two recordings. Very faint absorption signals from small amounts of light. That's one of the key messages from this, so it's not straightforward. You're dealing with very small amounts of faint light. But they do that, those two recordings to get rid of all the noise. So that's important. So they get the light from the star and the planet, in other words, the light travelling from the star travelling through the planet's atmosphere, and then they subtract the light from the star only, and that gives them the light from the planetary atmosphere as well only. Now, why do they do that? It's to get rid of all the noise that goes on from a star. A lot of stellar activity. Stars, they're pretty feisty little fellas. They've got flares going on, you've got sunspots going on, with less activity, you've got flares, you've got little filaments and folliculae, all sorts of activity going on. So, a lot of fluctuations, a lot of noise going on and false signals that could really screw up your data that you're interested in. And that of course, naturally gives false impressions of the properties of an atmosphere or chemistry. For example, you want to know, you're trying to analyse a planet and you want to know its properties. Is it a rocky planet like a super Earth that's mainly rocky with a nice hard surface that's habitable with a nice atmosphere? Is it covered in ocean, a Hycean planet? Is it just a big gas giant, a mini Neptune with no surface that's not habitable? So these are all sort of things that a star could upset your recordings and your observations. Its atmosphere. What is the temperature of that atmosphere? How thick is that atmosphere? What is the air pressure? Does it have clouds? Does it have winds? Does it have haze? These are all things that are able to tease out of the data on the atmospheres. But you get all this noise going on from the host star, and it's going to really throw everything out and confuse it. So they do this process to just try and get the light as much as they can just from the planet only. And once they've got what they think is reliable results, the benefits from that, they're able to look at potential biosignatures of life, in other words, chemicals that can be produced by light, not necessarily exclusively by life, but certainly that life can produce that gets their interest. A little flag goes up, such as oxygen, methane. Nitrous oxide is only made by microbes. Then there's dimethyl sulfate, which we'll be talking about shortly. That's on Earth is only produced by microbes. Then there's also stuff like clues to planetary formation. And there's two main ways, in theory, how planets form from the protoplanetary disk, the disk of gas and cloud around a star, either by what we call the core accretion, where you get little molecules building together, and you get little pebbles and stones and boulders and rocks, and slowly building up, accreting material to get a nice big solid core there that might remain as a terrestrial planet, or maybe then some ice forms on it, accretes onto it, then it gets to a critical size, and then it accretes some hydrogen and helium gas on board, and so on, to create a gas giant. So there's that, and then there's the idea of what we call gravitational instability, where you just get a whole region of the disk that just becomes gravitationally unstable and just collapses in onto itself with self-gravity and creates a planet from there. And if you see a lot, which they're seeing, a lot of CO2, methane, ammonia and water, that's the computer models that suggest that that planet was formed from core accretion, not gravitational collapse. And the logic behind that is that the accretion, you slowly build up and you get an accumulation of all these chemicals here that then are outgassed into the atmosphere of it, and you wouldn't get that process happening with it suddenly gravitational instability. So they can tell, that's the sort of information. Is there possibly life there, and how did that planet form? Just by analysing its atmosphere. Okay, so let's use an example, and this one's been in the press a lot, is exoplanet K2-18b, where a group recently in the UK announced to the world, and everyone got excited, oh, these are the best signs of life that we've had so far. So let's have a look at it here, and this is the James Webb, the data from its near-infrared spectroscopes, and here we have the amount of light blockage, and along here the wavelengths of light. And you can see here they found methane, some signals of methane, carbon dioxide, and here's this dimethyl sulfide, DMS, but just a very weak, not a very convincing signal of it here, and another one further out here. So this is all in near infrared, so it's going up to about 5 microns. So that was interesting. There's signs of methane and carbon dioxide, and when you get those two together, you start thinking, oh, there's a chance life could be there, because both those are made by life and also geological abiotic methods as well. But the two get consumed pretty quickly, get broken down pretty quickly. So when you see them both together, it's what they call disequilibrium. You think, it gets your attention. And then they say, oh my gosh, there's possibly some dimethyl sulfide in here that's produced on Earth only by marine plankton. So that really got their attention. But it really wasn't convincing, can you? I've seen, can you get excited about that? I can't. Look at those error bars as well. And I get excited pretty easy. And I couldn't get excited about that. That's dimethyl sulfide there. So you got your sulfur there, and you got some couple of methyl groups there. So for me not get excited, that's something. So what they did then is the James Webb, they looked at it in the mid-infrared wavelengths, which the telescopes couldn't go right through to about 12 micrometers. And then they found some what they thought was strong, well, they certainly are stronger signals suggesting the DMS, dimethyl sulfide here. So, that's looking interesting, and they did their analysis of that, which we'll come to, and declared, look, we've got strong evidence of a biogenic gas in the atmosphere of this planet. And there's a little bit of history. These results are being challenged and considered tentative only. So why is it so? You think, wow, look at these. Look, guys, look. Big hump here, and this is it. And the bottom line is, and what I'm going to talk about this, sort of some of the holes in this data, if you will, and I'm not so much getting at this particular set of data and what they've done with it or whatever, but what I am highlighting is this is a whole new field of science. There's no textbooks on it. No one tells you which model to use and which statistical method to use. So it's a whole new field. As I mentioned, you're dealing with faint bits of light from long distances, that potential a lot of noise in the data as well. It's not easy pulling. It's not black and white. It's not like looking at the sun and seeing your absorption lines. Oh, look what we've got, guys. It's a totally different ball game. So it is difficult. So typically, as I said, it's typically faint, it's distorted, and it's noisy. Look at the error bars. Whoa, look at these. Like big sausages sitting up there. Huge, big error bars. So, as I mentioned before, the spectral features here are due to the vibration and rotation of molecules. And as also mentioned there, just to qualify that, they are actually quantitized. So this, you can't get an infinite amount of rotation or an infinite amount of vibration. They are set levels. You think, why aren't you seeing discrete little levels in the infrared then? Because the signals, remember we talked about all the properties of an atmosphere, like its air pressure, temperature, winds, and so on. The signals are all influenced by that. How much vibration and vibration and rotation you get because of the Doppler effect. Once again, you might get a little molecule for that split second times given out a certain a particle of light at a certain wavelength because it's just rotated or vibrated in a certain way. But between doing that as it's rotating or as it's moving in the wind, you're getting a little bit of Doppler effect going on. Little wavelengths get shifted to the blue or back to the red and so on. So you got with all the winds and gas going on, suddenly you've got collisions going on. And of course, what happens when molecules collide, if they're in a bit of an energetic state, they collide with something else. They're no longer in that state. That state gets shifted up or down. So the states of the energy states suddenly get all blurred together as well. And what that does, it creates these, which you saw before, really broad, spread out signals, often overlapping with other chemicals. They call it data degenerative data. The data is just degenerated. Instead of being nice, even then you might think it's broadened out, but it's broadened out so much. And then you've got all these different chemicals that normally would have their signature, but this time they're all getting knocked around by winds and air pressures and so on. They're all starting to overlap with one another, and vibration, one might sort of be pretty close to a rotation of another molecule, and they're all getting mixed up and overlaps. You get this degenerative data going on with these big, broad, spread out signals. As you can see here, it's not like little absorption lines at all. So, with your raw data, what do they do with it? And the bottom line is they use computer models, and they can do one of two ways, the canonical or the retrieval method. And the one method is, the canonical method is, you make some assumptions about your atmosphere, properties of the atmosphere, and you get your data, and you try and use computer models. And there's various computer models to do this, to try and match up and get your best data. Or you can use the retrieval method, whereby you get your data from there and try and speculate or assume what your conditions in your atmosphere are. And you try and bring them together and get your computer models to find the best match. And often they'll repeat the process over and over again until they refine it down, and they get the best match to what they believe the atmospheric conditions are and what molecules are in there. So it's not black and white. It's a whole new science. There's various wind models and processes to use, and that is up for its debate. So as I put here, there's mixed opinions. These guys used one set of methods. They actually used, like a lot of them use hybrids between the two main methods, but there's various computer models. There's that's very labour intensive and not without its problems. There's various statistical methods you can use, and so on. It's not straightforward. So there's lots of different mixed opinions. Oh, you should have used that model. You should have done this. You should have used the statistical analysis of it. But hey, there are no textbooks. So some of the problems with this particular data, Ethan Siegel, he's a popular astrophysicist, also a science communicator. In his article here, his opinion was, as you're probably aware, they assumed it was a Hycean world. A Hycean world is where you get a sort of a big rocky core, like a super Earth, and then you get a global ocean of water right around it with a thick envelope of hydrogen. And it's a play on words because ocean and hydrogen, the Hycean world. And they applied that for their modelling data in the first instance. But they got their assumption it was a Hycean world from the Hubble telescope in 2019. As the Hubble telescope just peers a little bit into the near infrared, just a little bit, up to about 1.7 microns. And it was assumed to be water. And here's some of the graphs here leading up to 1.7 microns. And you can see here, look, it's all messed, but water at various wavelengths, one's water and one's methane. Methane and water at certain wavelengths, particularly at this range of wavelengths here, very similar, easy to get mixed up. And the Hubble team in 2019 got all excited. Oh, this planet's got water vapor. It appears to be a terrestrial planet from what we can tell by its parameters, and it's got water in there. Oh, it must be a Hycean world. And they assumed a lot of that for their modelling. But it is also, as Siegel said, look, you're talking a planet, it's got the mass of 8.6 Earth masses. It's got the radius, the size, about 2.6 times the radius of Earth's radius, gives it a density of 2.7. That really is sounding more like a mini Neptune rather than a rock solid Earth. What's Earth, 5.52 or something, grams per cubic centimetre. So he said, look, this is a pretty low density. They're really questioning whether it's a Hycean world at all. It most likely, his opinion, once again, the more papers you read, the different opinions you get. But so I've just plucked his out. His opinion was that it was probably a mini Neptune. In other words, just a gas giant, just smaller than the size of Neptune, with no water going on there at all. Because follow-up with the James Webb, as you saw those previous ones, saw methane, which you saw gets mixed up with water at the Hubble wavelengths, and CO2, but they detected no signs of water in there. So that was one, for example. Then there was a guy, Jake Taylor at Oxford. He's an astrophysicist and mathematician, and he looked at all the statistical, and he looked at those charts. The guys there were using Bayesian statistics, whereby you assume all your knowledge on a certain model, and then you add some more data to it, and it tells you statistically how relevant that is, changing stuff around. He looked at a lot of that data and said, look, these lines here look in sort of a Gaussian distribution, if you will, these little humps patterns here. So he used your straightforward Gaussian statistics, and he ran it through many, many, many different models and said 5 out of 6 of his models showed that statistically that's no different than a flat line. There is no signals there. So who's right? Who knows? And my point is not to say, oh, look how terrible is this, because these are just opinions. These are just opinions. And the other thing is to throw in here, not only to say it's unlikely, there's also a question if there is dimethyl sulfate. We know on Earth it's only made, as far as we're aware, is by marine plankton. So yay, it's a sign of life. But hey, they found dimethyl sulfate on comet P67. How did that get there? So there may be other chemistries going on outside of Earth that we don't know about, whereby abiotic means, non-living ways, that you can create dimethyl sulfate. So that throws another little thing in there as well, period of doubt. If you're interested, you can take a picture of your phone, but it's on the web page is on your handout, or you can watch the video afterwards if you like. These are really two really neat YouTube things. This one here goes on for about an hour with Martian colonist, he calls himself, and he goes through the retrieval model of how they get the data and how they best fit it to models. That's really, really insightful. That's really enjoyable. Dr. Becky, she speaks for about 20 minutes or so, and she looks further into this paper and looks further into Jake Taylor's paper and so on. And once again, that's very insightful, how there's no right or wrong at these early stages of this science, what models to use, how to approach this data, how to analyse it. It's not black and white as your normal absorption lines. So I threw in here as well, you saw, I don't know, almost all you would have heard that in the news, all the excitement and buzzing around from all of this, is that they talked about 3 sigma and 5 sigma and stuff, and it's the degrees of certain statistical confidence in the results. So I just plucked out the 2. They were sort of saying it was of 3 sigma significance. And you might think, wow, 99.7% chance that this information is correct, with only 0.3% chance that it's a false positive. But in science, that's not good enough. And that's just they would say, that interpretation, yeah, it's suggestive. You've piqued our interest in it, but it could still be a fluke. We're not really convinced. And these guys who really were being optimistic of what they say, their statistics showed there was a 3 sigma of significance. The gold standard for science is a 5 sigma, 99.9994%, which leaves you only about a 1 in 3.5 million chance of it being a fluke. And that's the gold standard. But as the 2 is which they're going to have to go back to this planet and look at it again with the James Webb, with another team, look at other ways of analysing the data. The real confidence depends on of anything in science, repetitively, independence, confirmation, and good experimental design. So they're going to go back, and not only are people pulling all this data and the way they've done it, they're pulling it to pieces. They're going to go back and have another look at it again, even with further instruments. There's more, the extremely large telescope is coming online in the future years. The Habitable Worlds Observatory, really higher resolution infrared telescopes and observatories are getting more specifically designed for this. They'll go back and look at from this. And don't get a disillusion with this. This is not scientists all having a big bun fight. This is science at work. This is science. This is what science does. This is science in progress. Science! This is what science is all about. People questioning and testing and seeing if they can repeat stuff. There you go. Okay, so that's enough of me rattling on. So let's sum up what we've talked about tonight. So yeah, atoms, light and spectroscopy, that it's the electrons have certain energy levels. They can go up and down depending whether they're absorbing or emitting light and energy. That gives line to your spectral lines, either your spiking emission lines or your absorption lines. They are fingerprints to tell you exactly how much, what atoms are there and what energy states that are there. The temperature of a star is determined by its peak wavelength, the shape of that spectral energy distribution curve, and how high intense the peak is and how the wavelength of light it matches up with. And of course, looking at the different atoms and the different energy states tells you the composition. The stellar radial velocity, how fast the star is coming away from you, and its rotation rate is all by using the Doppler effect, looking at the red and Doppler shifts in the wavelength of light you're looking at, see whether those little absorption lines are being moved over to the left or the right and measuring how much. The surface gravity, in other words, how dense and compact the star is down at its surface, or how strong its magnetic field lines. That's all determined by, once again, with your spectroscopy, looking at those absorption lines, looking at the broadening of them for the surface gravity and the splitting of spectral lines for the magnetic fields. And exoplanetary atmospheres, it's looking at the infrared, it's analysing the host star's light as it shines through the atmosphere of these exoplanets. It's in the infrared as opposed to these are predominantly in the optical wavelengths. It's a whole new field of science. It's tricky, but it's exciting. And we'll probably, I think Dr. Becky talks about it. Someone said to her, how are we going to discover life one time, extraterrestrial life? And it was told, it won't be just sudden a big announcement, oh my God, we found life. It will be, like we're seeing now at the beginning, it will be stops and starts. We think we've found life. No, we haven't. We think we have. Well, we haven't. And slowly, over probably a decade or two, more and more repeated science on particular planets. Oh, I think we've found it, because we can't go there and have a look. So this and that is the story of how an astronomer corrected a philosopher. Thank you. Any questions related to that? No, I think I've... Yeah.
Well, can you get quantities? Because you mentioned like most of the sun is hydrogen and helium. Can you get quantities from analysis?
Oh, yeah, from your trace elements and so, yes. And just go and Google that up. Yeah, yep, absolutely, yeah, yep. Otherwise, that's all good. Now, we thought for July's talk, because July, of course, is moon landing month. We haven't done it for 5 or 6 years, and I've got a whole new collection of slides and stuff we're going to have a nice pictorial going through all the moon landings and so on. We're going to have fun with that, nice big pictorials on the big screen. I sometimes go and sit in the audience myself, only put a picture there just so I can see it too on the big screen. So we haven't done that for a few years, so we're going to have some fun with that. And so we'll see you all for that. Thank you very much, and drive home safely. Thank you.